Okay, so let's talk about the secant graph. It can look a little intimidating, right? You've got these weird U-shapes and all these breaks in the line, but what if I told you there's a super simple trick to mastering it? The secret is actually hiding in a function you already know really, really well, cosine. Let's see how they're connected.
So, here's our game plan. First up, we're going to uncover secant's true identity as cosine's reciprocal twin. Then I'll show you a simple 3-step blueprint that makes graphing it an absolute breeze. After that, we'll put our blueprint to the test, I'll show you how to sidestep a really common pitfall, and finally, we'll discover where this seemingly abstract function actually shows up in the real world.
All right, let's kick things off with Section 1, cosine's reciprocal twin. You know, the best way to understand something new is to connect it to something you already get, and that's our entire strategy here.
You know this one, of course, the smooth, predictable wave of y equals cosine of x. It just kind of goes back and forth, nice and easy, between 1 and -1. This simple wave is the foundation for everything we're about to do.
So, here's the big question. What on earth happens when we graph the reciprocal of that simple wave? Well, the result looks completely different. It's this series of U-shaped branches. But believe it or not, this wild-looking graph comes directly from that calm little cosine curve. Let's dig in.
Okay, this right here, this is the whole game. Secant of x is just 1 divided by the cosine of x. That's it. This one single relationship is the key that unlocks every peak, every valley, and every single gap in that secant graph.
All right, let's get to the good stuff. Our 3-step blueprint. This is where we turn that complicated-looking graph into a simple recipe you can use every single time, no problem.
Okay, here's the blueprint. It's so easy. Step 1, you just lightly sketch your cosine wave as a dashed guide. For step 2, look for everywhere that guide hits the x-axis, wherever cosine is 0. At each of those points, you draw a vertical line. Those are your asymptotes. And finally, step 3, you just go to every peak of your cosine guide and draw an upward U that just kisses it, and at every valley, you draw a downward U. And that's it. That is the entire process.
And this process basically reveals all the key features for us. The period is 2 pi, which makes sense, right? It's just following its cosine guide. The asymptotes pop up exactly where cosine is 0, and notice the range. The graph only exists above 1 and below -1. And that empty space in the middle, that makes total sense now because our U-shapes can only launch from the highest and lowest points of the cosine wave.
Okay, so theory is one thing, but let's actually put this blueprint to work. We're going to walk through a few quick examples to really make this stick.
Let's start super simple. What about when x is 0? All we have to do is go back to our main definition.
Well, we know cosine of 0 is just 1, so secant of 0 is simply 1 over 1, which is, of course, 1. And if you picture the graph, that point is the very bottom of that U-shape sitting right on the y-axis.
Okay, let's try a trickier one. Pi over 2. Why is this undefined? Well, the clue, once again, is what's happening with cosine at that exact spot.
Right, so at pi over 2, cosine hits 0. So when we try to calculate secant, we end up trying to divide 1 by 0. And you just can't do that. It's impossible. That division by 0 is precisely what creates the vertical asymptote. The function just shoots off toward infinity because its denominator is getting closer and closer to nothing.
All right, time to put it all together. How do we use our blueprint to sketch one complete period of the secant function right from scratch? We just follow the blueprint, step by step. First, you dash out your cosine wave from 0 to 2 pi. Next, find where it hits 0. That's at pi over 2 and 3 pi over 2, and draw in your vertical asymptotes. Then, at the peaks of the cosine wave, at x equals 0 and x equals 2 pi, you sketch your upward U-shapes. And finally, at the very bottom of the cosine wave, at x equals pi, you draw your downward U, and just like that, you have one full, perfect period.
Now, before we wrap up, we have to talk about the one mistake almost everyone makes when drawing this graph. If you can avoid this, you're golden.
So listen up, this is super important. The U-shaped branches are separate, distinct pieces of the graph. They get closer and closer to the asymptotes, but they never ever touch them or cross them.
So please, don't try to connect the dots and draw some kind of continuous wavy line. Remember, the function is undefined at the asymptotes, so there's a literal break in the graph. Also, don't forget that empty band between y equals -1 and y equals 1. The secant graph lives entirely outside of this space. It only ever touches the borders at -1 and 1.
So why should we even care about this? It's easy to think of these as just abstract drawings in a math book, right? But the secant function actually shows up in some pretty incredible real-world situations.
And that's a totally fair question. When does this actually get used in the real world?
Well, one really big one is structural engineering. When you're designing massive structures like suspension bridges, the math that models the forces involved has to be absolutely perfect.
So check this out. Here's an amazing way to picture this. Imagine the main cable on a suspension bridge. As that cable gets pulled tighter and tighter, closer to being perfectly horizontal, the tension on it doesn't just increase, it skyrockets towards infinity. That sudden, infinite spike in force is exactly what the secant function's asymptote represents. So the next time you see that vertical line on a graph, remember, it's not just a line. It can model a very real and a very powerful physical force.